Dark matter sounds like the name of a thing. It sounds as if astronomers found some hidden cosmic substance, locked it in a conceptual box, and moved on. That is not what happened. What happened is stranger. The universe kept failing the same test. Galaxies were rotating too fast, galaxy clusters seemed too heavy, light was bending around invisible mass, the large-scale cosmic web looked as if visible galaxies were hanging on scaffolding we could not see. Again and again, the math said the same thing. Whatever we are looking at, the stars and gas are not enough. That is the real dark matter problem. Not that scientists discovered a mysterious object and gave it a dramatic name. It is that the universe appears to contain far more gravitational structure than ordinary matter can provide, and that extra gravity refuses to go away. Why this matters? This is not a side puzzle about distant galaxies. Dark matter sits inside our biggest model of reality. If the leading picture is right, then most of the matter in the universe is not made of atoms, does not shine, and has never been directly identified in a laboratory. The part of the cosmos that feels familiar may be the bright surface layer, not the main construction. Dark matter matters because it changes the answer to a basic question. What is the universe actually made of? Start with the simple expectation. If most of a galaxy's mass is concentrated where most of its light is, then stars farther from the center should orbit more slowly. That is how gravity usually works in the picture people carry around from the solar system. The farther out you go, the weaker the pull should become, and the slower objects should move. But when astronomers measured how fast stars and gas orbit in spiral galaxies, the outer regions often did not slow down the way that simple picture predicted. The rotation curves stayed flatter than expected. That matters because orbital speed is not decoration. It is a direct clue about how much mass is doing the pulling. So either the visible matter was only part of the story, or gravity itself behaved differently from what the standard picture assumed on those scales. That fork in the road still defines the subject today. Rotation curves would already be a serious problem by themselves. But dark matter became the leading explanation because the problem does not stay confined to galaxies. Move up in scale to galaxy clusters. These are not loose neighborhoods, necessities. They are gigantic gravitational systems containing hundreds or even thousands of galaxies, enormous reservoirs of hot gas, and deep gravitational wells. When astronomers measure how galaxies move inside these clusters or examine the temperature and behavior of the gas trapped there, the same tension appears. There seems to be much more mass present than normal matter alone can explain. Then light enters the story. According to general relativity, mass warps spacetime, and warped spacetime bends the path of light. That means massive objects can act as lenses. They distort the appearance of more distant galaxies behind them. Sometimes the effect is dramatic, producing stretched arcs and multiple images. Sometimes it is subtle, visible only statistically across huge surveys. Either way, lensing lets astronomers weigh structures that cannot be weighed on a scale. And the lensing maps keep saying the same thing. The galaxy motions say, there is more mass here than telescopes can account for in stars, gas, and dust. One of the clearest examples is the Bullet cluster, where two galaxy clusters collided. The hot gas, which holds much of the ordinary matter, was slowed by the collision. But the main mass mapped through lensing stayed aligned more closely with the galaxies than with the gas. That separation is one of the strongest pieces of evidence that the missing gravity is not just hidden ordinary matter. It behaves like something else. Now widen the view even further. The early universe was not born with galaxies, clusters, and filaments already assembled. It began much smoother, with tiny fluctuations in density. Over billions of years, gravity amplified those tiny differences. Dense regions pulled in more matter, stars formed, galaxies formed, clusters formed. The cosmic web emerged. But the timing matters. To build the large-scale structure we see today, the universe seems to need an additional source of gravitational scaffolding that does not behave like ordinary matter. Normal matter interacts with radiation. Early on, it was too tightly coupled to light to start clumping efficiently on its own. Dark matter, in the standard picture, begins gathering into structure earlier. Ordinary matter then falls into those gravitational wells later. That is one reason scientists often describe dark matter as the framework or scaffolding of the cosmos. Not because anyone has photographed a literal invisible skeleton, but because simulations reproduce the large-scale universe much more successfully when this unseen component is included. Recent maps have made that idea easier to visualize. In January 2026, NASA highlighted web-based dark matter mapping that traced a web-like pattern of dense regions linked by lower-density filaments. The point was not that Webb directly saw dark matter glowing in space. The point was that the distribution of galaxies and the distortion of light from background objects let researchers reconstruct where unseen mass must be shaping the scene. This is one of the strangest parts of the whole story. Dark matter may be invisible to telescopes in the ordinary sense, but it is not hidden in the casual sense. It leaves fingerprints everywhere. Gravity has time to work. Once the evidence builds up, the next question becomes unavoidable. What kind of thing could do this? The standard answer is cautious, some form of matter with mass that interacts strongly through gravity, but not or barely through light. In other words, not atoms, not familiar gas, not dust, not dark clouds waiting to be imaged better. Something outside the ordinary inventory. That opens the door to candidates. For years, one of the most famous was the WIMP, the weakly interacting massive particle. WIMPs were appealing because they fit naturally into several extensions of known particle physics and could, in broad outline, produce the right cosmic abundance. After decades of increasingly sensitive direct detection experiments, WIMPs have not shown up. That does not disprove the entire dark matter idea. It does mean one elegant candidate has taken repeated blows. So attention has widened. Axions remain a major possibility. They would be extremely light and require very different detection methods. Sterile neutrinos show up in some models. Hidden sector particles open the possibility that dark matter is part of a larger unseen particle world. Primordial black holes have been proposed in some scenarios, though current constraints leave only limited room for them to explain all dark matter. The landscape is broad because the evidence tells us more clearly what dark matter does than what dark matter is. We are working backward from gravitational behavior toward the identity of whatever produces it. There is another route through the problem. Maybe the missing gravity is not missing matter at all. Maybe the law of gravity itself needs revision under certain conditions. Modified gravity ideas try to explain the mismatch without introducing a new invisible substance. Some of these approaches can reproduce aspects of galactic behavior surprisingly well, especially in regimes of very low acceleration. That is one reason the debate never vanished. The data did not simply crush every alternative overnight. But the challenge gets harder as the scales pile up. A successful replacement has to do more than address one class of galaxy measurements. It has to explain galaxy clusters, gravitational lensing, the growth of large-scale structure, and the full cosmological picture with comparable power. That is where dark matter, as a framework, still tends to outperform the alternatives overall. So the cleanest answer is not dark matter is proven beyond question, and not scientists made it up because they were confused. The cleaner answer is this: the gravitational discrepancy is real. The leading interpretation is unseen matter. Alternatives exist, but they carry a heavier burden when asked to explain the full range of evidence at once. This is where the mystery becomes more interesting, not less. Scientists do not yet know what dark matter is made of. They do not know whether it is one particle, several particles, or something more exotic than the current particle menu suggests. They do not know whether it has tiny self-interactions that only show up under special conditions, or whether it is almost perfectly collisionless. They do not know whether the standard cold dark matter model will survive every small-scale test as observations sharpen. There are also unresolved tensions closer to the scale of individual galaxies. Some observed structures appear less dense or less cuspy than simple simulations once predicted. Some satellite galaxy counts and internal distributions have fueled years of debate about whether the model needs refinement, better treatment of ordinary matter, or something more fundamental. And then there is the detection problem. If dark matter is a particle, why has it been so hard to catch directly? That may mean the interaction strength is far lower than many older models expected. It may mean the mass range is different. It may mean we have been looking with the wrong strategies. Or, in the more disruptive possibility, it may mean the true answer is not sitting inside the standard search categories at all. This is why dark matter remains one of the healthiest kinds of scientific mystery. The evidence is not vague, the uncertainty is. So what is dark matter really supposed to be? Right now, the most honest answer is not a name of a particle. It is a job description. Dark matter is whatever is supplying the extra gravity that helps galaxies hold together. Clusters outweigh their visible contents, light bend around hidden mass, and cosmic structure grow the way it does. We know some of the rules it seems to follow. It does not shine. It does not behave like ordinary matter. It shapes the universe on scales so large that entire webs of galaxies appear to rest on it. And yet the thing doing all of that still has no confirmed identity. That should change how you picture the cosmos. The visible universe is not the whole stage. It may not even be most of the architecture. Stars, planets, nebulae, and galaxies are the luminous parts we can point to, but the deeper structure may be governed by something that never glows at all. It is like walking through a city at night and mistaking the lit windows for the building. The windows are real. They tell you something, but they are not the load-bearing frame. Dark matter may be the load-bearing frame of the universe, and if that is true, then one of the central facts of reality is that the cosmos is shaped, at the largest scales, by something we still cannot name with confidence. The natural next step is not just asking what dark matter might be. It is asking how scientists map something they cannot see in the first place, because that is where this stops sounding like an abstract hole in physics and starts looking like a very concrete detective story.